It's my great pleasure to introduce tonight's inaugural lecture. I arrived at King's just over a year ago, actually a year and about 3 weeks now. And amongst the very, very first conversations I had concerned the planned recruitment of a new professor in telecommunications. I was told, and I completely agreed, that we needed someone who was energetic, intellectually sophisticated, with an outstanding research reputation, and at the same time, someone who was entrepreneurial in their approach and who had a willingness to work with industry. Characteristics that I'm proud to say I've discovered over the past year that we really prize in the School of Natural and Mathematical Sciences. Many of you here today share that combination of that ability to work at the deepest level in terms of research, but also to explain your research in ways that's exciting to the outside world there. And that's what, this wonderful combination of characteristics, we found in Mischa Dohler, our new professor in wireless telecommunications and our head of the centre, that famous centre for telecoms research there, of which we are very, very proud indeed. But of course, Mischa is no stranger to King's. Following his degree in physics at Moscow State University, he came to us in 1999 to take his MSc at the centre, and then undertook his PhD in virtual antenna arrays, brackets, capacity enhancement techniques in 2003. He stayed with us as a lecturer for 2 years until 2005, and I hope he is the proud holder of a PG Cap certificate there. At the same time, he was also taking training courses in IP, spin-offs and business ventures, and left us to become senior research expert at CTTC and to found his own company, Word Sensing, and I have to say these are the words on his website there, an award-winning business focusing on industrial automation and instrumentation for smart cities, smart structures and smart field markets, which is very, very successful in the marketplace. But along with this success track record in innovation, he's published extensively in IEEE journals and is the co-editor of a special issue on Internet of Things, Architecture, Protocols and Services in the IEEE Sensors Journal, though I notice the deadline is the 31st of January. So when you've finished here, there may be 1 or 2 things to do there. And it's for these and his other many accomplishments that he was recently appointed to the Fellowship of the IEEE, something of which King's is enormously proud there. It's a privilege and an honour and a real pleasure to have you back with us, Mischa, and indeed to have your family with us as well there. Can I now invite you to deliver your inaugural lecture on the dawn of connected machines. Ladies and gentlemen, Professor Dohler.
It happened at the very end of World War II, when Roosevelt instructed every single city in the United States to be connected with a highway. This started one of the biggest infrastructure projects of modern times and essentially facilitated supply to meet demand so much easier, and therefore stimulated one of the strongest economies to date. It was that connectivity between city A and city B, B and C, C to D, D to B, B to Z, which allowed this to happen. It's not the only exercise we did where we connected things. Another one appeared a few decades later when we started to build the internet. Again, we connected computer A with computer B, B with C, C with D, D with etc. We built a whole mesh of computers which went on to become the internet. Again, stimulating a renaissance of economy and trade worldwide. Today, we're trying to replicate this connectivity paradigm within the grid. We're trying to build the next generation power grid, a smart grid, where power does not flow just in one direction, along some lines. We're trying to build a grid where power then can flow between entity A and B and C. And we build a mesh of power grids, allowing essentially, again, for this connectivity paradigm and ideally economic benefits. Now, what I find very powerful comparing all these connectivity exercises is that they all resemble. They resemble graphically, graph theoretically, statistically. There are a lot of commonalities here. Whether it is the neurons in the brain, whether it is the city roads we are connecting houses and shopping malls, whether it is the internet itself, social graphs, or whether it is actually the universe. This is a picture of a very distant black matter connecting stars down the road. So there's a very great similarity here between these connectivity and exercises. But what I find extraordinarily striking is that they share three commonalities, really. The first commonality is that all of them allow A to talk to B and B talk to A. Bidirectionality is so important. A second commonality is that they're all, in a sense, packet switched versus circuit switched. Packet switch means I'm sending small entities of something down the road rather than having a line reserved for certain things to flow. An example is when we introduced the highways with the cars, we essentially replaced a circuit switched train line by means of a packet switched car transport. It just allowed it to be so much more flexible. Internet, the same thing. We replaced a circuit switched infrastructure where phone calls were made along fixed lines with an operator switching here and there. And in the end, we had the internet, which was a packet switched entity. And another interesting insight from these connectivity issues is that actually the processing power of every single node doesn't matter. It just disappears within the paradigm of the network. So whether I have a supercomputer or a very small sensor network there, just doesn't matter as long as I have them all connected. And from that, we observe that actually once I surpass a certain threshold of connectivity, the actual level of connectivity just disappears. The network itself disappears. We're not talking about a network or road anymore. We're talking about the supply chain. When you order something on Amazon, you don't think of a truck driving down the M25, the M4, down to your home. You just think of a supply chain of a service. The same with the internet. You don't think anymore of a bit and byte traveling actually for literally a cable, going to the internet, going to an edge router on the coast, going into the waters of the Atlantic Ocean, a cable into the US and out there, and we don't think about it anymore. The infrastructure has become invisible. Completely invisible, and it allowed us essentially to decouple this infrastructure from the services we offer on top. Now, the internet is not the last and the most beautiful thing we have seen. There's more coming. We are expecting this world of ubiquitously connected sensors, objects, things, processes, you name it. It's a cyber world where you will have probably more objects talking to you than friends, real friends. That would be by 2020, 2025, and my lecture today is about showing a little bit where we are today with this vision, which is so scary to some and so inspiring to others, and what we need to do to reach that very milestone at the end of the road. Now, where are we today? I'll show you a few applications. These applications exist as of 2013-14. I'll start with very different sets of applications. I'll start with the smart city application. It's a very hot town phrase, everybody talks about it. The problem is nobody really knows what it is. Now, my company works in the smart city space, so I can reveal you a few secrets here. So smart city is really about two giants here. It's about the smart guys and the city guys. Okay? So the smart guys are the IBMs, the Ciscos, Department of Informatics of Kings. And the city guys are the NSLs, the SWATCOs, the Telvents. So the smart guys, you've heard all these companies' names. The city guys, you've probably never heard of them. But still they own the majority of this infrastructure in this world. These are the ones who put the parking machines, who actually draw the lines, who own the traffic controllers, the traffic lights. They own the actual city. Now, they don't want to concede space to the smart people, to the IBMs and the Ciscos, because that is their space. On the other hand, the IBMs and Ciscos, they think, hey, you know, the only way we can really make this city space smart is by having our technology there. So we're currently observing a fight of titans between these two very large communities. And when you look at the city itself, you realize they're broke, they have no money. So to get anything meaningfully going there is very difficult. So you need to find a smart city application which allows us to bootstrap that market. There are not so many. Bootstrapping means whatever additional service you offer, you can leverage some finances on top, and with these finances you can finance maybe other projects which wouldn't generate so much money. And when you look at the return of investment exercises in a city, there may be 2 or 3 examples which are useful. There's parking, there's maybe street lighting, there's watering, water irrigation in the southern countries, and maybe smart metering in the buildings themselves. So this is what you got. Now I'll give you an example of parking. It's a pretty mundane example a lot of companies talking about is the Westminster has started to trial this type of technology. So what we do here is we put sensors in each parking spot, which would allow us to detect reliably and in real time down to seconds whether the parking space is free or not. Now that information goes to a processing center and you would get it on your smartphone or on your GPS, whatever you use. Now it's beautiful. So the official story is we tell to the citizens, we allow you to drive more efficiently to the parking spaces which are free. You pollute less, it's less headache, it's less stress, etc. In reality, and this has to stay within this room, of course somebody has to pay the parking. So what we do is we give that information to the traffic wardens who can actually correlate parking events with payment events and figure out if somebody hasn't paid up, and hey, you know, we need to send somebody there to do the fine. So no matter what you do, is whether you educate the people to pay up or you actually award some fines, the city would generate an additional revenue, which is up to 30% more what they earn at the moment. It's quite a lot of money. So that is what pays this party. The other application is smart street lighting, which lowers the cost of electricity, etc., etc. Another one example I want to give you is out of the smart home space. So that has also taken off as of 2014. That's a beautiful example here. So what it is, I'm not sure anybody knows about it, but that is a product offered by a company called Nest. It's a smart thermostat. So you put it in your home, and it does what we have been doing all the way along. It would regulate your heating system. But there's something about this device which is different to what we had before. It is a smart device. It learns. It's literally an intelligent machine which learns about your habits, your behavior, and regulates the heating system accordingly. It saves you a lot of bills. On the other hand, it's a bit costly because it has been designed by some ex-Apple people. So you can buy it for some $300, that's for years. And if a week ago you had $3.2 billion, you could have built the company. But Google bought it first. So here you go. Enormous market. Okay, so that is really the home IoT market here, because Nest not only regulates your home space, but it also has access to you as people. And this is why Google wanted them. Another application here, it's a bit of a funny one, it's the smart diaper. So what is in there? There's a water sensor, liquid sensor in the diaper, and it would connect to the internet. And whenever your kid or your baby has peed, you would get an SMS, etc. So you collect statistics, you can change the diaper, etc., etc. So you get the idea. This is the quantified self. I've given you an extreme example. We have other things. You can buy this Fitbit. You can buy a lot of things which would quantify us, ourselves, our performance, our most precious meat. Another example here comes from infrastructure. I put it up because in London lately a lot of roofs coming down, so I thought I'd give you an example. My company has done it. We instrumented what is the equivalent of the Royal Albert Hall, but in Barcelona. And it's the Palau Sant Jordi down there, and we put a lot of real-time instrumentation sensors here just to make it a safer infrastructure. And I want to show you an excerpt from the video which explains to you how this machine-to-machine sensing technology actually works.
Barcelona's state-of-the-art venue implements state-of-the-art monitoring technology. Palau Sant Jordi is a multi-purpose indoors installation that is part of the Olympic Ring complex located in Barcelona. It was opened in 1990 as a symbol of modern Barcelona and is considered a masterpiece of modern architecture and engineering. Palau St George's roof consists of a giant metallic web combined with glazed ceramic tiles. The goal of the project is to establish real-time monitoring of the loads applied to the roof's structural system. The weight applied to each individual load point and the load distribution and equilibrium in the entire structure. World Sensing solution consists of 153 foil strain gauge load cells to control all load points in the structure. These load cells are read every 5 seconds by 21 load sensing wireless multi-channel data loggers. The load sensing wireless system creates a smart, auto-organized mesh network that reaches the gateway, where all data is stored, processed, and sent from the sensor network to clients and world sensing servers for 24/7 management and control. The system is managed in the control center.
The original of that project was that Lady Gaga gave a concert there, and she must have hit a resonance tone. So the whole structure started to vibrate, and they were really scared it would just fall off. Now, instead of waiting, they instrumented that, and a tender was put out, and we won that tender because we had a very strong competitive advantage. We were the only solution at that time which was wireless. It just turns out that having a wireless asset in your end-to-end turnkey solution gives you some financial, operational and other benefits which proved to be the winning factor in this specific tender and all the subsequent tenders which came out of that. To understand that, what I've plotted here is the cost versus time of the different ingredients in machine-to-machine sensor network solutions today. You have a computing element, you have a communications element, and you have a human element where you install things, etc. As you can see, computing power and processing power is really decreasing over time. The only thing which is increasing is actually the human cost and the cabling cost. So cables are becoming more and more expensive. We're talking about copper increasing every now and then in value. So if you get rid of these cables here, you not only save in human installation costs, but you also save in actual hardware costs, up to 90%. And that proved to be the big difference in this specific tender. Now, we are not the only ones who have realized that. What I did here is I collected the names of some of the top 100 companies by market capitalization. And I took everybody else who was below 60 and who wouldn't relate really to wireless technology. And it turned out there's some very big names in here which would actually make wireless engineering solution their bread and butter to really be able to be competitive in the market. Let's start with the supply chains. Walmart. RFID, you need to monitor where your stuff goes. You need RFID sensors tracking your goods, etc. So they're using wireless technologies today. Oil and gas, that's a market we are in. With my company, we are providing wireless seismic instrumentation. So what is happening is that these companies, whether it's Schlumberger, whether it's BP, etc., they're trying to find resources, oil, gas, minerals, coal, etc. They need to take a picture of the subsoil. Now, how this is done is they would take seismic sensors, stuck them in the earth, and you would need loads of them, 10,000, over a field of 10 kilometers by 10 kilometers. They used to be cabled. So the cable cost is enormous. The crew exercise is very complex. It's very, very tricky. So what we developed is a wireless solution. We would connect those 10,000 data loggers to the internet wirelessly, therefore lowering costs significantly. You go on, telecom companies in there. There are the electricity companies in there which are using the development of the smart grid to use that type of technology, etc., etc. And only down here, you see computing, hardware companies, IBMs, and Hewlett-Packards. So these ones up here are actually really making use of the wireless technology. Now, I love that graph from General Electric. General Electric put it really to the point here, quantifying the cables by using this industrial internet. So connecting small sensors, objects on their machinery, whether it's the airplane engine, whether it's a valve on a refinery. If you do the maths, they figured out that the financial gains are just enormous. They're billions of dollars. And this is only if we improve the efficiency by 1%. And I can tell you we can do better than that. So there's enormous gain we can have here. So 2014 is a breakthrough year. It's really a breakthrough year when it comes to the mobile and wireless data generation. It's the first time in history we would produce more data on the run, mobile, whether it's your iPhone, whether it is your laptop, whether these are the machines you use to instrument something, they will generate more data than the actual desktop computers we have been using traditionally. It's not the only thing which is a breakthrough here. We have also more smartphones in use than the rest, and we will have more machine-to-machine traffic generated than the traffic generated by tablets. So you see that there's an interesting shift of data composition and data nature which needs to be addressed. Now, how do we do that? With a suitable architecture. So this is what we really work on within CTR, and CTR has been, for the past 20 years, instrumental in helping developing the 2G, 3G, and 4G architectures, and today we're here with the 5G architecture. And to understand what it really implies, let me just show you a very simple technology graph here where I show the rate versus the range, and you will observe some familiar technologies. So let's start with the low rate and low range. So what you have there is Bluetooth. Everybody's carrying Bluetooth around. It's a type of technology. When you switch it on, it just wouldn't work. But you have it. All the mobile phones have it today. And it is supposed to mean to enable essentially communication over short distances. Then you have a technology you're very familiar with, which is Wi-Fi, short range and high rate. And this is really going now to the megabits per second, gigabits per second with the latest standards developments. Then we have a technology which is my cellular, 3G and 4G technology, the usual handsets with which you do the mobile phone calls, etc. And that is the opportunity. That's the opportunity we're really trying to get on, which is the machine-to-machine traffic, connecting sensors, objects, whatever you need to connect. But here really, we don't need a lot of data. It's very low rate. It's exactly the opposite from what we have been doing so far. So we're trying to enable YouTube downloading and uploading. Here we just want to say, hey, my Coke machine is empty. Or my parking sensor, my parking place is occupied. It's just a bit. Very often it's a single bit you're sending. If you encrypt it, it's maybe 16 bytes, but that's it. Very little data. But a lot of devices do that. So we have to design nowadays a system which will allow, essentially, to embrace established systems like Wi-Fi, like the legacy system 3G and 4G, and enable new stuff like the cellular machine-to-machine. And that is what 5G is really all about. It would try to embrace that and come up with a single architecture to make this happen. Now, in terms of challenges, it's all still a little bit wobbly what 5G is all about, but we figured out one thing we really need to make sure this time is cost. Okay? All the other systems we designed, the cost came kind of last. It was first the engineers who did the exercise, and then the economists came in and said, hey, look, we don't break even in our return of investment sheet. So therefore cost has to be in this from day one. We need to make sure it's available. If you realize central London, it's very difficult to make a single phone call which lasts longer than 5 minutes. You always get a dropped call, you always get rejected. So it just turns out that in some regions of the country you have a very good availability in terms of making phone calls, data calls, but in others it's a big problem. So we need to come up with an architecture which would get around this problem so we don't have the outage and call admission control problems. Another thing is the delay. We would love really to connect our control valves, our actuators. We would love to instrument a refinery, very critical machines. Now to do that, you need to make sure if something goes wrong, the alert is sent very quickly up to the processing center, comes down to the robot, to the actuator, something is switched off or switched on. You want to make sure that this is within milliseconds. So for that, delay needs to be minimized. We can't wait like we do now to establish calls, etc., etc. Then we have peak rate requirements. We are just tired of running behind the computing community where, you know, data rates of gigabits per second are very common. You can do a lot of stuff with that. Wireless has always been lagging behind by at least an order of magnitude. We want to overcome that in 5G. We really want to be at par with the wired connectivity. So we have an end-to-end type of system which facilitates it all. And then, of course, scalability of my machine-to-machine solution. So a few things are coming up here in the 5G design. And for you to understand, I just drew you very quickly how the telecom data flow is, or the voice call flow. So what you do is you have your device on the end, might be a sensor, might be a machine, your Bangalore mobile phone coming out next year, your laptop. It connects via the wireless access network to your base station. So you see these antennas very often. These are base station antennas. They communicate wirelessly with each other via a so-called backhaul network. And these are these dishes here, the microwave dishes, which would absorb the data until it gets to some routers, some switches. So I purposely didn't depict here the internet. These are machines somewhere which act as routers, cable in, decision where it goes, cable out, until you reach the end device. So this is what's happening. And these are the paradigm shifts we're experiencing as we speak. We will have a software-defined system end-to-end. Software-defined means we're trying to have as little in hardware as possible and as much controllable by software as possible. The idea, the dream really is to have 5G installed on every single base station on the planet with a single mouse click. You don't want to send your engineers actually setting out new base stations, adapting the tilt, doing your hardware configuration. Very expensive. It doesn't scale. So why don't we have software technology which allows us to reconfigure that from the office? And this is coming end-to-end, including your mobile phone, including the base station, including the core network components, etc., etc. Software-defined end-to-end. Another paradigm we are seeing now, end-to-end virtualization. So we're virtualizing components. We are putting functionalities together, whether they are hardware or software, putting it all together, which allows essentially much better scale and allows also a concept like virtual operators, etc., 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 to be put in place. Another paradigm we see is cloudification. So we're trying to follow the computing industry here and try to have my radio access network cloudified as much as I can, meaning very important constituents, parameters, etc., decision-taking on interference are being stored and handled in a cloud. You know, at the moment they call it the RAN cloud, but this is what it is. You try to assemble and mass a flux of information from the network in a single place. Another paradigm we see is edge intelligence. So we're trying to push out now a lot of the decisions to the edge, because it turns out we can take decisions so much quicker. The system is so much more resilient if you have an edge intelligence. And along this line here, this edge intelligence is currently gripping the whole community in telecoms. We're trying to build this truly end-to-end cognitive system. And cognitive really refers you to a system which is not opportunistic. So it's not a system which reacts on input-output kind of rules. It's a system which would learn. It would intelligently adapt. Okay? Cognoscere in Latin means to learn. It would follow this typical Heiken cycle, as they call it, where you would acquire some information, you would do some intelligent decision-taking, and you would act on the information, and you repeat this cycle. So an example is if you start deploying a lot of sensors, they would adapt to the environment because they are already femtocells, microcells, mobile phones communicating, etc. It turns out that these algorithms are very lousy. They're very lousy in terms of convergence speed and convergence precision. So the system turns out to be fairly unstable if you use purely cognitive algorithms. So a while ago, we started to look into this, and we coined what has become the dositive network. And dositive here really comes from docere Latin, to teach, which is replicating a paradigm which we do so well in our society, that we have schools, universities, where we would teach knowledge. So the idea was that, okay, my intelligent edge devices would not learn independently for themselves, but they would share the knowledge. We would have master nodes, teachers, distributing knowledge, and have therefore a much better convergence and stability of the system. I'll give you the example with Q-learning. So Q-learning is a model-free machine learning method. It's a very simple thing, really. It has an input and an output matrix. Let me give you the example of a kid trying to learn to cross a traffic light. So input is traffic light is green, traffic light is red. These are the two input levels. And output is the kid walks or the kid doesn't walk. So as a kid approaches the traffic lights on red, it tries to cross a street, then the the mother would punish the kid, and therefore the feedback would say, hey, there's no reward, there's a punishment. The value which corresponds to this input-output relationship would diminish. On the other hand, as the kid approaches the traffic light, it is green and it walks, the mother would say, well done, and we would increase that value which corresponds to that combination. So therefore the kid would learn with a simple input-output relationship table and the feedback mechanisms, and we can expand that to more input states and more output actions. If it gets too big, we involve some neural network, but the whole idea is to build these tables. Now, how Q-learning can be transposed to DOS session is that we would take these values, these neural relationships, these Q values of the table, and we transpose them to the other devices. So a kid, now another kid which comes to traffic light would not need to learn this by repetitive exercises, but would rather be told directly about how to behave in these scenarios. So this is how we did, and it worked really well in the femto and machine-to-machine type of environments. Now, having all that, this system facilitated, we clearly move on. So the question is, what's next? So we have built the infrastructure, collected data, what's happening with the data? So here comes a little bit the future, what's happening with this data. So big data, a lot of people talk about it. Now I can't give my definition from my TED talk from last month, so I'll stick to this one, which I adapted to this audience. So big data is like doing research. Okay, lots of people talk about it, very few people actually doing it, and even less people doing it really well. So this is what really big data is today. People would just, use it as an overarching frame with the danger that we would actually abuse it before we have solved something. Okay? What it actually entails is something like this. So we have an input here of data, we have a processing of data, we have an output of data. So the input of data is sensor data, the stuff I've just talked about. But it can be other data as well. It could be data from the internet. It could also be data from you, people, crowdsourced data. So you're sampling all that. This data has very different characteristics. So the sensor data is very reliable data because we have installed the sensors, we've calibrated them, we've gone through a very rigorous certification process, but it's very expensive. On the other hand, the crowd data is very cheap, often for free. You get a lot amount of data, but you don't know what's the quality of the data. So we need to kind of compensate, we need to find this sweet spot where quality of data becomes a reliable quantitative measure. Now you have data going then in, and then you start processing the raw data. You build knowledge, you build wisdom, and you take decisions. And that's a really interesting part because big data mostly stops here. Okay? So what you do is you collect statistics, you put them in a PowerPoint, you're actually doing anything with that. You're just amazed by the insights. But it would be a really interesting challenge to do something about this, to act on that, okay? Whether you're controlling a robot, whether you're controlling an actuator, changing a street light, whether you're giving some guidelines to people, changing a light, etc. The real paradigm, I think, would be to go beyond the big data and do something about it, which would be then the big action. So what we're doing essentially, we're closing the data cycle, okay? So we're closing the data cycle where we collect data. So this would be the sensing people. We deliver the data. These would be the telecom people. We actually store the data. These would be the computing people. And we would put essentially the big data capabilities and analytics on top, which are the machine learning people. And then we would act on that, which would be the robotics people. So it turns out that Informatics and Kings had actually the whole composition of the team of doing this big data cycle, addressing this 21st century challenge. Let me give you an example. A very specific example from Barcelona where we use this type of paradigm. So my company would deliver real-time parking information and real-time traffic flux in Barcelona. The city would assemble this data. They would also take crowdsourced data from Facebook and Twitter feeds, and they would also take information from the internet, be it weather information or sports information. So it turns out that Barca is playing Real Madrid. It's going to be a rainy day, and build on past statistics, we know the city is going to be a complete mess because everybody is coming by car, it's raining, we have problem zones here, we have problem zones there, and this is when the big action comes in. Building on previous statistics, we suddenly start to control traffic lights. So the Siemens traffic light controls are being controlled so that the flux of cars wouldn't go a certain down the road, but would go another road. We would guide the people to free parking spaces, etc., just to make this experience, this whole quality of living so much more desirable in Barcelona when these type of events occur. Another hot topic now is the topic of privacy, really. And I want to touch on this very quickly because when we talk about data, and particularly data which is collected from us as people, the issue of privacy always comes up. And this graph is inspired, is inspired by a discussion which I had with John Crawford from Cambridge and Vince from Google, the founder of the internet. So what we see here is the level of privacy versus time. And it has been argued that actually until a certain point, level of privacy was virtually absent. You know, when we lived in caves, we lived in small villages, etc., there was no notion of privacy really. Everybody knew what everybody else was doing. Along came the first industrial revolution, which did something very important. It massified the place where we work, and it massified the place where we lived, and it separated both. So we became an anonymous entry on both ends of our daily journey, and therefore the whole notion of privacy actually emerged. Along came the internet, the third industrial revolution, spiced in a little bit with the NSA, Snowden, and you end up essentially, again, with the level of privacy which we had before. So there's an argument that privacy is kind of a luxury we enjoyed over the past 200 years, but should not be a commodity we should be further enjoying. Not sure we agree with that, but I want to give you an example which I think you should understand. Let's look at Google. So Google clearly collects a lot of data from us. Okay? Now, they're using this data to leverage it on some business models and get money from that. And with that, essentially, they pay for the whole data infrastructure and the search capabilities. Now, running my own company now, I understand somebody needs to pay for everything. Okay? So the alternative is Google doesn't collect any data, and you pay for every search you do. Now, the question is whether we would be where we are today with this type of model. I presume we wouldn't be, because this ability we had it before when we could call the information services, but we pay for that. Okay? So therefore, this free access to the searching capabilities around the globe has enabled this economy to grow exponentially. But of course, Google needs to finance somehow the business, pay their people so they can pay their families so their kids can go to school. Now, clearly what we don't want is that personal data is being used. Okay? What we want is that data is being used, big data is being used, so we assemble this data, but what we really want to do is we want to separate very clearly the technical data from the personal data. So I want to know, Google may want to know, and Cafe Nero wants to know that somebody there, somebody famous had a coffee with somebody there. What they don't want to know is that this specific person had a coffee with this specific person there. So separating the personal data and the technical data is a very big challenge. We have it actually. Technically speaking, we can do that. And the institutions who are doing that, or the entities, are called escrows. So information goes in, third-party escrow would separate very clearly, the technical data from the personal one. It would say somebody has been in Euro, but it has an ID X, and somebody else with an ID Y. And the personal matching between both is kept separately. And it turns out that the British government is trying to go down this road. They don't want to have a big database with everything in there. They're trying to have many distributed databases, and they want to keep personal information out. But of course, they need to match somewhere the technical ID to the personal ID, which they want to be handled by third-party entities. Maybe King's would be a great institution to host these type of escrows. Okay, my last point now is on something which I think is as equal as sorting out the privacy. It is about understanding the value chain. Okay? The value chain of data, the value chain of open data, big data. The question I'm asking here is, what is the dollar value, the pound value, euro value of a single bit of data you generate? Nobody knows. And this uncertainty, essentially, is holding back a lot of big data capabilities. I give you an example of my company. We have been requested to make our data available freely. I wouldn't do that if I don't know how much the single bit of parking, traffic, seismic information actually costs. If I know how much it costs, I can price it and would make a 50-50 deal or whatever, but I have no idea at all. I don't know whether it is data which a bit costs 1 cent, $1, $100, $1 million. We don't know. So understanding the value chain, I think, is really instrumental of getting the big data picture going. So I've been working on this ever since I came to King's, and I want to share some early results with you. To do that, I want to introduce a few notions here. So what I've defined is a big data source, or a big data destination. I call it role. I then defined a big data flow. Okay? G. I then defined a big data transaction field, which is E. And I defined a big data monetization field, which is H. I then defined a resistance of big data uptake. So that is more like technology. So imagine this to be a representation of whether you collect the data wirelessly, which would have a low epsilon, or with a cable, which would have a higher epsilon, or with somebody carrying a USB stick, which would be an even higher epsilon. So that is the kind of resistancy factor. And we have mu, which would represent essentially my ability to do transactions in the data field. It's a regulational thing. It's a policy thing. It's what needs to be handled at economic levels. Okay? So we have all that. Where E and H are two different things. So, and J as well. So this is really literally bits and bytes flowing, the J. E is the transaction I do due to bits and bytes flowing. It's like saying, I sell you, 10 kilobytes of data. That is what E is. H, on the other hand, is my actual financial transaction. Okay? So this is like the dollar value I give to these 10 kilobits of data. Now let's sit down and think about how they relate. It is very clear that, data value, the transaction field is being generated. If you take an enclosure around, a big data source or big data sink, which is proportional to my data I have in there, my row divided by the ability to collect this data towards that surface. Okay? So if you mingle a little bit around and we follow the footsteps of a pretty famous guy, we end up with that equation here. Okay? So the divergence of E is equal to rho by epsilon. Now we take it further, we figure out that money cannot be printed unless, of course, it has a value generated. So again, if you take a certain surface, within this surface, you can't print money really. If some money goes in, some money has to come out. Okay? So that is what essentially would characterize my second equation, which is divergence of H is 0. We then go on, we look at the demand-supply equations, which would essentially characterize the relationship between, transactions and monies behind those transactions. We realize that if something becomes very expensive, my demand is higher than my supply being my data. So there needs to be a minus relationship in there. And clearly something has to change over time. Well, I'll come back to this in a moment. But if you write it down, this is what you end up with. So the curl of E, so the financial transaction or the transactionability of big data around the data flux is inversely proportional to the change of H multiplied by the ability to do these transactions. And the fourth equation is, now those who are skilled in the arts can't really imagine what it will look like, but it essentially says that the transactions I generate around the data pipe, a big data pipe, is proportional to the actual big data which goes through the pipe, plus, of course, the transactions, the transactional big data field, which I'm doing with E. So we end up with something like this. So the curl of H is the actual data plus my data transaction field changing over time, and normalized by my ability to actually reach the big data. Now, incidentally, these equations were developed in part about 200 years ago, just 7 floors down from this very room, by a chap called Maxwell. And with these equations, he showed us something which was not visible at that time: waves. We've seen the antenna at the beginning, we've seen the antenna at the very end, but we didn't know how they would connect, that there's something. And again, maybe, with the data is the very same thing. We see that there's data being generated on one end, we have a demand on another end. How they relate in terms of transactional monetary fields is something we may just explore with these type of equations. So if you're interested in that, if you're a mathematician in this room, a physicist in this room, if you work on antennas and you're interested in big data, please join me in this journey of exploring these equations. Thank you very much.
Any questions? Your talk was absolutely great until you started talking about big data value chain. I am extremely skeptical of your model. If the original problem was to try and put a value on the data, why don't we do it the simple way by letting the law of supply and demand decide the price? I think that the problem that you have with generating the data for the Barcelona, for instance, is that you have only one client. If we had a market, we wouldn't have this problem started.
Okay, so the question was, I'm not sure everybody heard it, is there was some doubt about the model on the big data value chain. Why invoke Maxwell's equations, not something else? Okay, so are you an electrical engineer by background? No, okay. So we have something called the Ohm's law, okay? It's actually a side result of Maxwell's equations. Now, the Ohm's law requires a wire and applies voltage, relates voltage, current, and resistance. And that would be exactly your demand-supply stuff. It's what you see, what you can measure easily. What I'm trying to explore here is to go beyond that, the invisible, something which I cannot answer even in my company. I don't know what is the first-order value of my 1 megabyte of data, or actually 1 terabyte of data I generate in world sensing every day when I sell it on. What is this value as this data is being processed and sold on? What is this value? How does the value propagate in space and time? Where again, you know, we are differentiating here the curl operation, the diff operation is differentiated over space, and the temporal differential was clearly a differential over time. This has to be taken very carefully. It's not literally these notions, there could be, but space could be a neighborhood relationship, okay? And time could be an opportunity. So it is something which has to be taken, you know, maybe in a specific big data space. We haven't explored that. But what I'm saying is the simple demand-supply type of equation that you know from economy, they would be, the equivalent would be Ohm's law. And I would be happy to explore this offline. Yeah?
Other questions? Yeah.
Mischa, this presents a very exciting possibility in the future, but I know people are worried about it. And just some words about that. If we look at history, human societies have an incredible, well-established tendency to fight wars and kill one another, and that isn't going to stop because that's human beings. So I think there is a genuine fear that this whole system might become very vulnerable to electronic warfare and the like. We've seen already the Stuxnet thing, which wrecked the centrifuges in Iran, and for sure that's just a start. And the things the military are thinking about in electronic warfare are far, far ahead of that. Should we be worried?
Yes. Please be worried. The more you're worried, the more research we can do. So, okay, so okay. Theoretically, you could probably protect anything you wanted to protect. So the security, cryptography, etc. algorithms, they're all there. They're sound. Okay? And I was involved actually in quite a lot of security standards bodies, where in the end of the day we figured out, hey, you know, if it's not for the NSA, but in theory, mathematically speaking, you can rebuild the system, which is probably pretty much secure, unless maybe some new quantum-like of computers come in, but let's presume they're not here. The big problem, though, are the policies. How do companies, how do governments actually put these protocols in place? And this is where the problems start, because it's not only that they would, you know, they're not capable of doing that, but also systems have become so complex that really trying to find every single loophole in that has just become so difficult. And I agree with you. So we have to be worried. Literally, we have to be worried. On the other hand, of course, it enables us a lot of things to do which we couldn't do before. So I believe it will be a thin line where hopefully research can tell us where to go.
Thank you.
Mischa, thank you very much for a fascinating talk. I'm still trying to get to grips with the very last section of your talk, so apologies if I've misunderstood. But one of the issues I grapple with is, I'm a statistician, one of the things that I grapple with is that data grows in value the more it's used. So how are you incorporating that sort of concept within your equations? Because I don't see how that fits within a Maxwell model.
Okay. So I probably would work out of the guts because, again, probably would need time to be redefined as usage. Okay, so you would differentiate rather across usage of data. I'm not sure how it would work out. On the other hand, I'm not so sure that this generally holds. So I'll give you the example of alarms. So alarms, France, for instance, is now rolling out a nationwide network where every single alarm which you see here on the ceiling needs to be wirelessly connected to some central base, etc. So when something happens, the fire brigade can be there very quickly. Now, that is a big data exercise, but the data you use here is 1 bit, okay? And you actually really never want to use it. So I'm not sure there's a general model of saying, you know, data becomes big and useful the moment you start using it. I think there's a lot of stuff out there where actually it's exactly the opposite. But I'm not sure how we could put this all into one model, so let's talk about this here. But just feeling-wise, I mean, from the originals, I've taken you through very quickly here. There's some longer documentation which we worked on also in a different context with my friend Adonis Kallis a while ago. So there's some reason to believe that these type of models hold, at least in an abstract sense. Yeah.
More questions?
How do you assign a vectorial variable to some scalar quantity like the transaction or some monetarization?
With the direction.
I mean, how do you define the direction? I mean,
yeah, so in this context, well, so in this context it would be literally the spatial direction, okay? So I'm literally, okay, but this was for simplification. So I'm saying I'm here, I have a data source, my data loggers, which I showed you before, producing X amount of data, I'm firing them off to the north. Okay, so literally it's a spatial. But of course, what I said is we need to see how we can transform that to a different space, which would be the space of connectivity. So you don't want to shoot that to the north, but actually to the guy who makes use out of this. Okay, and again, time not necessarily being literally time in seconds, but something which is like a type of opportunity, which is advancing. Okay. Yeah.
Yeah, it's similar to the ones the lady. I have somehow under the impression that you consider data as being as like a commodity, whereas from my layman point of view, the value comes from the processing that you do on the data. So where am I getting wrong?
I think you just brought to the point. I think it is a commodity. Data is a commodity. It will be a commodity like oil and electricity and information in general. That's why I think it holds so well. Yeah.
It's dangerous. I feel that there's some kind of a Heisenberg equations. So when you act the value to data, probability balance change. In general, propagation has been so vectorial patterns of propagation determine the value. So this is a value. So to me, it's like Heisenberg.
Well, the Heisenberg principle would state, you know, that something either you get one or the other. Okay, so in nature it would be to get the age of the tree, you need to kill it. Okay, either you have a living tree or you know the age, or the particle, you know the speed, but you don't know location, etc. It's interesting you bring this up. I need to digest that, how this would relate. But the spatial, the change of, you know, ability to actually do financial transactions, okay, over space opportunities on networks, etc., is very well modeled with Mu, actually. Because, of course, it's not a constant, literally. It is a constant which depends on, often not time, but at least on space, okay? So you can put it in, okay? So the epsilon you have is really also an antenna theory. The epsilon typically only relates to the very same antenna rod you use to do the radiation, the dipole, okay? Once it goes off, the electromagnetic wave will not have any epsilons, just epsilon zero free space. Now the Mu in this case would of course be a quantity which actually changes over distance, and there's an enormous amount of literature we could use readily from electromagnetism, physics, antenna theory, etc., to help designing optimal policies. You know, how do you shape essentially an optimum transmitter of data, an optimum destination emitter of data, a destination source, a sink of data? How do you do matching between them, etc.? So I think we could just really make use of this body, and the variability of the opportunity distance of the Mu would become a variable of that. So you would put it inside a differential, actually. That's very important.
Okay. Thank you for very nice stuff. From physics point of view, this question is related to if you have an electromagnetic wave and you have an antenna or a nano-antenna, or we call it metamaterial, and that interaction of this electromagnetic wave with this material can cause different effects. One of them is super resolution, and another one is invisibility. So in the case of informatics, if we have such a material, or if you have such an environment or atmosphere, you might miss the data because the electromagnetic waves or the light, let's say, bends around that particular area, and you don't detect, because what you detect is from the top and the bottom. So that kind of, I don't know if you can call it this
okay. It's a little bit freaky for my understanding. So we're trying to find a general kind of theory of putting things together. However, I think that would be a great example of detecting data fraud. Okay? Because probably you would be able to figure out, you know, if something is wrong in the input-output relationship, that something has been manipulated either in the transaction fields or in the data transmission field. Okay? I'm not sure it mimics what you're saying. I need to, maybe in the break we can discuss that, because I'm not quite sure I understand. I have done physics like ages ago.
I think we have time for only one more question, and that's gentleman.
I was interested in the temporal aspects of collecting and using and analysing big data, sort of thing like Google Spanner's aimed at, and Hadoop and things like that. And in Spanner they're even using atomic clocks to synchronise data in different places around the world. I wonder if you have any views on that sort of area.
Okay, it goes a little bit beyond the actual framework we're trying to build. Yeah.
And the Maxwell's equation version, what's root mu over epsilon? Is it some velocity or something or other?
That's interesting. Okay, yes.
I mean,
so again, it relates to this question. I would presume, I'm not quite sure this, but you would, you know, data theft, data abuse, you would probably be able to detect these type of invisible things fairly quickly.
Very interesting.
Yeah. Okay, thank you.
Well, there might be a question from the young lady at the back. That would be your last. Is that hand up?
I don't understand.
She's my daughter, and this is my education.
So I just have a quick announcement to make, and that is that you're all invited to share in Mischa's great success in the reception that's around the corner in the old Anatomy Museum, so just around here behind where we are. And the second thing is I want to ask you to join me in applauding Professor Mischa Dohler on his inaugural.